Welcome back. Today we want to have a look at what happens when light passes through a single and a double slit. Now we know light is a wave, and we've already looked at some of the properties of waves, and one of them in particular is called diffraction. Diffraction is a property of waves that happens when waves pass through an opening or around a barrier. And we've already seen that the dimension of the opening compared to the wavelength is really the only critical factor. If the opening is roughly the same size as the wavelength, you get lots of bending and lots of diffraction, as we see in this diagram. So these waves are traveling from the left. They start as planar waves or straight waves. They pass through the opening and they bend, and this is called diffraction. Now we want to look at what happens when we add another opening. So let's do that now. So I've added a second slit or a second opening. And now these blue waves, they're not only going to travel through the top one and diffract, they're going to travel through the bottom one and diffract. Just to keep track, I'm going to put the bottom one in red. So the bottom one will create its own diffraction pattern, which I'm going to look at with the red lines. And now we see we have two properties. Not only do we have the diffraction or the bending of the waves through the slit, but these two waves are overlapping each other and causing interference. Where the two crests overlap, so where a red and a green line overlap, we know we have constructive interference. And in between the green lines would be a trough, and if a trough and a crest overlap, we have destructive interference. What does that look like overall? Let's have a look at an actual picture. So here we see a more detailed diagram. The slits are separated by a distance d, and outside the one slit we see the waves are traveling in circles, just like my green waves in the diagram that I've drawn. But here they've drawn the whites as the crests and the dark lines as the troughs. Similarly on the right hand side. Same style of wave except it's shifted over. So if we follow these crests through, we can see that the two crests overlap, the two white lines overlap right in the dead center. So we would call that an antinode because it's two crests overlapping, creating constructive interference. Similarly, we see two black lines right below it overlapping, two troughs. That's still an antinode because it still represents constructive interference. So constructive interference for light simply means a larger amplitude light wave. So we would expect right at this point for the light to be very bright. And if you move over a little bit, we see that a crest, a white line, is actually overlapping a black line. So we'd see some destructive interference at this location representing a node. So you'd see a dark spot here. And overall, what ends up happening is you get this alternating light, dark, all the way along in a symmetrical pattern from the center line out. It would look as follows if we shone laser light through a double slit. So we see three different colors of laser light. Obviously it's passed through some sort of diffraction grating or double slit, and we see the bright spots representing our antinodes and the dark spots representing our nodes. And we want to look at this in a little more detail as to why the nodes and antinodes occur exactly where they are, and come up with a formula that represents this phenomenon. Finally, one more thing before we go, let's look at what this would look like graphically. In other words, if I was to place a screen along the top here and we'll have the light waves hit the screen, we would see this pattern that we see in the black image at the top. We'd see a bright central max, dark spots on either side, then bright, then dark, then bright, then dark. But we want to represent that graphically. We can see from the picture here that the center is the brightest and they gradually get dimmer and dimmer and dimmer as we move off to the left and off to the right. Graphically, it would look as follows. So on the y-axis, on the vertical axis, is the intensity or the brightness of the light, and on the x-axis is our distance from the center. They measure it in terms of theta, theta being an angle from the center line at the bottom, which we'll talk more about in the next video. So again, we see the brightest section right in the middle, then dark, then a little less bright, then dark, then a little less bright, then dark. So our nodes are located exactly at theta 1, theta 2, and theta 3, and our antinodes are in between all of those values with the brightest central antinode right in the dead center.